we are looking at program verification, and we had the small language of while programs, which is what we wanted to verify. So what I did was I looked at this while programming language. I defined a small syntax. So the moment you define a syntax, you have to define a semantics, and this consists of basically an identity function, an assignment, sequential composition, a conditional, and a looping construct, basically an unbounded looping construct. So all bounded looping constructs can be obtained from the unbounded looping construct. Basically the semantics of any programming language is usually treated as the program as a sort of a state transformer, which in our case in the context of first order logic works out to valuations for some valuations under some model usually, and for the purpose of verification what we are essentially looking at is the first order theory of that model. So in general, otherwise the programming language is actually independent of the model. The constructs of the programming language are actually independent of the model, but you could take any kind of model. But normally of course we take integers as, let's say, the model. I mean, since that's up to some abstraction, that is what most machines actually implement. So a simple general purpose programming language has this functional semantics, which I did last time. And then the other thing that I wanted to, in the context of first order logic, we can also view programs not just as state transformers, but as predicate transformers. So as something that takes an input property and gives you an output property. But that essentially means that you're talking about, it's still going to act as a transformer of states from some valuation v to some valuation v prime. However, what we are talking about is whether we are taking this valuation from an input property, from essentially a subset of valuations which satisfy a certain property phi, and we are essentially saying that v prime would be belong to a subset which is characterized by the set of valuations which satisfy, let's say, this output property of psi. Right. So then we defined the notion of partial correctness assertions and total correctness assertions, and let me correct some mistakes I made last time. Okay, so let's look at this example of factorial. Let's assume that our signature is some superset of these things. I am including the factorial symbol also there because I am going to use it in my verification. But you can, and the other thing is that I am taking the entire set of integers as a countably infinite set of constants, constant symbols, which is usually the case, except that we in an actual machine we are bounded by a finite, only a finite subset of z. But for the purposes of verification, let's assume this is an infinite set of constants. However, the set of terms that you get is still only countably infinite, even if you take this entire set z as a set of constants as part of the signature. Okay, so the model, as we write more and more complicated programs, our signature will actually increase. So for the purpose of this factorial program, it's enough to have this much. So that's why I've written the signature sigma is a superset of this. So it contains at least these operations. Let's take this first program P1. P1 actually has this condition x is not equal to 0. Okay, and under this condition, x equals x0, P1, P equals x0. Actually, this should be x equals x0 greater than or equal to 0. Then P would be the factorial of x0 prime, right? But this partial correctness assertion is correct in the sense that if x0 were negative, okay, then this program would not halt. Okay. Because this program checks exactly for x being equal to 0. So, if x is negative, it will still enter the loop and it will keep decrementing, it will keep multiplying something to p and so on and so forth, but basically it's never going to terminate. Okay. So, in that sense this partial correctness assertion actually specifies the partial correctness of this program P1. So, this total correctness assertion however is not valid because of the fact that there is no guarantee of termination and this program might actually not terminate. So, even if you, so if x naught is negative, then of course the program is not going to terminate. So, this total correctness assertion would not be valid. Okay. So, that's the first thing. The second thing was actually what I gave yesterday as the program last time. So here I actually have the assertion x greater than 0 as a condition, and then both the same thing, the same specification holds as both partial correctness and total correctness, because this program is guaranteed to terminate under the integers always. Yeah. Okay. I mean, so that subtle difference between partial and total correctness is something that has to be maintained. However, this specification is not technically complete. Okay. It's not technically complete in a certain sense, which is that it only gives you half the story. The other half of the story, when x naught is negative, is something that it does not say, right. This notion of technical completeness is, I put it within double quotes, but you should actually look at the slides of my programming notes, where I have defined it more formally in the context of type systems and so on and so forth. But so normally what we expect is a technically complete specification. So, in that sense, this specification here are slightly weaker than what might be called a technically complete specification. So, the basic idea here is that every program is correct. It only depends on what the specification is. Okay. So, this program is so a technically complete specification under the integers essentially would specify what happens when x naught is both negative and non-negative. And you actually get this interesting case that when x naught is negative, then you get your product to be 1, right. You get this, so it is not really factorial, I mean, and we are not programming the gamma function. Okay. So, this program is not really the factorial program in a strict sense, yeah, because of the fact that for negative integers it gives the value 1, right. Okay. So, but however, as I said, every program is correct, it only depends what your specification is. So, if you give this as your specification then that is a technically more complete specification under the integers, right. Okay. Right. So, we were looking at proof rules. So, here is the first proof rule for epsilon. Epsilon is basically the identity function. So, as a predicate transformer, it leaves the input predicate unchanged as output. So, that is why you have phi epsilon phi, and I am only giving partial correctness proof rules here initially. So, the assignment, as I said, this V prime is actually, a variant, an x variant of V, in which x gets the value t, right. So, now this would satisfy, let us say, supposing this belongs to a set of valuations which satisfies a predicate psi, then the only alternative, the only input possible predicates that satisfy that can act as specification for this assignment are those in which, if you had syntactically replaced x by the term t, then you get a predicate that is true. I mean, so that subset in which x is actually replaced by t by substitution. Okay. So that's here's where the main difference comes between this while programming language as a theoretical programming language as opposed to a while programming language which is going to be implemented on a machine where x is going to be the name of a memory location rather than the name of a term. I mean, so the differences between L value and R value then become prominent, right. So what we are actually, the abstraction we are doing is that we are ignoring the fact that these variables that we are talking about in actual implementations are actually names of memory locations, and therefore they are containers, they are not, so they are not associations in a functional sense, they are not just abbreviations for terms, they are not just names for terms, they are actually containers, and so therefore the notion of an L value and R value is something that we are ignoring completely. Okay, so that's so in that sense our model is a purely theoretical model and does not actually conform to the notion of memory in a standard von Neumann architecture, right. And so you cannot extend this you cannot extend this while programming language to one with pointers and expect to get proof rules also in exactly the same way. And in fact, that issue of dealing with heap structures and pointer evaluations in memory is still a subject of certain kind of research. It's not easy to get elegant programming logics by which you can prove completely the properties that you normally expect from let us say object oriented programs or programs with pointers and so on and so forth, because the notions of L value and R value are very crucial there. Okay, so this notion, this particular assignment essentially treats this a variable as just another name for a term. Okay, and that's why the substitution is possible. Otherwise, under L value and R value conditions, pure substitution would not be possible. Okay. Okay, composition. So essentially, what we are saying is you start from a state satisfying a predicate phi, and the effect of P would be to give you a state satisfying some psi, and the effect of Q would be to give you on that state satisfying xi would be to give you a state satisfying psi, right. And that composition is essentially functional composition written as this proof rule. The conditional, of course, is just that you take this state satisfying phi and that can be divided in half between those that subset which satisfies the condition chi and the other half which does not satisfy chi, right. So I have put in a huge gap just to emphasize the difference. So essentially what we are saying is you execute this program, you execute this conditional if chi then p else q as if it starts from a state satisfying chi and phi, then it will take you to some post condition to a state satisfying psi through p, and if it starts in a state not satisfying chi but satisfies only phi, then it will take you through q again to the set satisfying psi. So the conditional allows a branching of the division of the input predicate into say two subsets, into partitions the input into two subsets. Okay. Finally, the loop, the proof rule for the loop, and one of the things that has always been the bugbear of most programmers is understanding the notion of an invariant. So essentially, if you look at this proof rule, what we are saying is there is this state located in phi. There are two possibilities, either chi is satisfied or chi is not satisfied. If chi is not satisfied, of course, then what happens is it actually nothing happens, it remains in this state. I mean, the effect of the program is to do nothing to it. But if it is in a state, if it starts from a state satisfying phi and chi, then it comes back to some other state, maybe satisfying both phi and chi, or it goes to another state satisfying phi but not chi. Okay. Now, this looping can happen as often as possible, and this phi therefore actually is a sort of I mean you can think of it as, you can think of that while loop as an if then else with an infinite unfolding, an infinitely nested if then else which has infinite exit branches depending upon the number of iterations of the while loop. Okay. And this phi, this loop invariant, is essentially a disjunction of all those things that guarantee zero iterations, 1 iteration, 2 iteration, 3 iteration and so on infinitely. So, that is actually an infinite disjunction, but what you want to do is that you want to capture that infinite disjunction by what you call an invariant property, right. So, these invariant properties are but of course, what these invariant properties are what make your understanding of the loop actually quite complete. Yeah. In this way, there are some trivial invariants, like the predicate true itself is an invariant anyway of every loop. Yeah. But unfortunately, that does not help you prove the program. Okay. So, what you require is a fairly strong invariant property. So, the choice of a fairly strong invariant property which allows you to prove the program is what you are usually looking at. Yeah. Okay. We will come to that, but more importantly, most often your specification is some phi and some psi, and the relationship between phi and psi is not that of is not necessarily that of implication. Yeah. So, there is a weakening rule called the consequence rule. So, this is the only logical rule which is not which is not structurally inductive, in the sense that here you are actually using the theory of first order logic completely. So, take a look at this. So, here the picture essentially says that supposing I have got a specification phi p psi. So, I want to prove that this program P satisfies the specification precondition phi and postcondition psi, but I am able to prove a stronger property. Okay. And what do I mean by a stronger property? I mean that supposing there is a phi prime which is weaker than phi, and there is a psi prime that is stronger than psi. The notion of strong and weak is just related by implication. So, if phi implies phi prime, then phi is stronger than phi prime. Yeah. So, if I can prove that from a larger subset of states, I am always guaranteed to go to a smaller subset in the output, then I can claim that from this smaller subset, I am always going to some element in this larger set, right. Yeah. So, this is a weakening rule, and in fact, in the context of so this is what allows you to go from loop invariants to specifications. So, if your loop invariant is some phi I, and you are supposed to prove that this while loop actually satisfies some phi and some psi, it's precondition and postcondition, then all you require is that this phi imply this phi I, and this phi and not chi imply that psi that you are looking at. So, you still have to find a strong enough invariant, But having found the strong enough invariant, you relate it to the phi and psi of your original specification through these logical implications. Now, these logical implications are essentially things that require a proof, preferably an automated proof, but in our case we will just do a hand proof of let us say a program, right. So, what these phi arrow phi prime and psi prime arrow psi are essential components of a given starting from a given specification, going to an implementation and proving its correctness. These are essential components. So, normally what happens in modern program verifiers is that you have a separate first order logic theorem prover and you farm out all these implications to that theorem prover, so that proves it in the first order theory of integers or whatever structure is your underlying model, and the results and the results of that come. So, what your actual program verifier does is it just gets these triples, and all the connections between the various kinds of triples have to be done through the theorem prover, let us say a first order logic theorem prover in this case. Yeah. Okay, so we will see how these rules are applied again by, so here is a summary of all these rules of partial correctness. Okay, there's no difference, this is just to put them all in one place, it's the same. The only difference is that there is the bracketing rule. This is of course purely syntactic, and what we are saying is that brackets do not have any particular significance. Yeah. So, we just I am sorry, this should have been a psi here. I have written phi here, it should have been psi in both the numerator and the denominator. Okay. Now, however, now there is this question of total correctness, right. So, if you look at all the basic constructs except for the while loop, termination is guaranteed in all constructs except when there is a while loop. So, that's obvious. So, now so therefore, the proof of total correctness and therefore of termination can actually be separated out from the proof of partial correctness by proving termination separately. Yeah. And so, what we do is we have to define some measure called the bound function. Okay. And let me call that beta. So, beta is actually a function of all the program variables, right. So, which means you basically take the free variables of your program and beta is some function about them, such that so essentially the domain of this function beta is the set of all tuple values of the program variables taken in some order. Okay. Take all the program variables in some order, form a tuple, look at all so essentially it is a Cartesian product, okay, that is the domain. The range of beta should be some well ordered set, which means it could be an infinite set, but it has a bound below. So, it is well ordered, so there has to be an ordering relation. So, let us call that less than, and of course, the converse of less than is greater than. Okay. It is bounded below by some least element. For the moment, let me call it 0. Basically, you take any countable well ordered set, that countable well ordered set can be placed in one-to-one correspondence with a subset of the naturals. Okay. So, I am not saying, so that is why I am using this 0 here, that is a sort of typical element, it need not be 0, it could be some. So, you take any well ordering set, any well ordered set, it can be mapped onto a subset of the naturals such that the well ordering, the less than relation on the well ordered set corresponds to the less than relation on the naturals. Okay. And this well ordered subset of naturals of course has a least element, and that is the bound that you are looking at, right. Okay. So, I am for the moment I am just calling it, I am just using 0 as, I am using a red 0 to say that this red color indicates that what we are talking about here is not exactly related to everything in the, it may not be related to the domain of structure of the model on which the program is based. So it may, so in the sense that if you were to take some program, let us say on some data structure with no arithmetic in it, let us say you are just doing list processing or some such thing, yeah, with no arithmetic, but you can still get your bound functions and so on and so forth in arithmetic in terms of length of that list, length of the list that is left to be processed and so on and so forth, right. So, this red color indicates that the domain, the range of B need not necessarily lie within the same model of the program variables. It could be different, and in particular it could be so you may not be dealing with natural numbers at all in your programs, but however your bound function would still involve counting, let us say, or at least it can be mapped onto a counting problem, which, so therefore it goes down to it can always be mapped onto just the termination aspect. This bound function can be mapped onto some subset of the naturals under less than, yeah. Okay. What this bound function needs to guarantee, what is the relationship it has with the program variables? One is that when this invariant property and the condition are both true, then this bound function should evaluate to something other than the bottom element of your well ordered set. Okay. So, it should be somewhere higher up. So, that is this greater than 0 that I have written here. And whenever this bound function is 0, or whenever it reaches the bottom of the well ordered set, the bound of the well ordered set, it should definitely mean the negation of the condition of the while loop. Okay. Now, notice that these are actually one way implications. Okay. So, one thing is that it is quite possible that this condition becomes false even though the bound function does not reach the bottom of the well ordered set. Okay. That is possible. And if the bound function is positive, that does not necessarily mean that the condition should be true. Okay. If you want to understand these things, just take something like GCD, right. Okay. Let us take the GCD program. I do not have to write it out. We all know how to do GCD, right. So, that the GCD traverses down essentially given initial set of naturals x and y, both of them positive, it travels down a well ordering. Okay. The ordered pair x y keeps reducing according to a certain, let us say, lexicographic ordering, yeah, of on pairs, and it never touches 0, but it terminates as soon as the ordered pair is the two elements of the ordered pair are equal, for example, right. And so, therefore, the fact that the bound function never reaches in that case the bottom element of the, but your range is still in a well ordered set. So, this is, by the way, range B ordered, okay, yeah. Actually, I should have said that B is this beta should be an injective function into a well ordered set, yeah. Okay. But so that's so these two implications are carefully chosen to satisfy only the forward properties and not necessarily the reverse properties. So, you can terminate the loop before you reach the bottom of the ordering, and if you have reached the bottom of the ordering, then it does not mean that you are I am sorry, If you have not reached the bottom of the ordering, then it does not mean that you have any more iterations to do. Okay. But if you have any iterations left to do, then you should not have reached the bottom of the ordering, and if you have reached the bottom of the ordering, then there should be no more iterations to do. That's the way the bound function has to be designed as a measure, and this is this can be very trivial in certain cases, but it can also be quite complicated in certain other cases. I'll show you where it is. There is still an open problem regarding these bound functions, which I will let you know. It actually came as a problem of number theory, but we can always translate it into a problem of programming. Yeah. Okay. So now our termination rules are exactly like our partial correctness rules, except for the this exclamation mark indicates termination. Yeah. Except for the while rule. So what we are saying now is, again I am using red because my measures of termination may be different from the domains I am using for programming, right. Okay, so I have a loop invariant, I have a condition, and I have a bound function of the program variables which I am writing as v vector, which has some value b naught, which is greater than the bottom element of the well ordered set. Okay, and each execution of the body of the loop maintains the program maintains the invariant property phi. It may not maintain the condition chi, but what it does do to the measure is that the new measure, the new value of the measure on the new value of the program variables should be guaranteed to lessen, to traverse down the at least one step in the well ordering. Okay. So, if you started with an initial value of b naught, now beta of v evaluated should give you something less than b naught. And if you guarantee this, then what we are saying is that this loop will always terminate, because this measure cannot go below the lower bound of the well ordering, and when it does terminate, the condition would be false. Right. Yeah. So this is it's a beta is of course the bound function satisfying these properties. Okay. Now let's just look at this factorial and let's just do a quick proof. Okay. So what I have done now is this typically I should have written them as triples, right? But under sequential composition, the right hand side of the kth, the post condition of the kth instruction is often the precondition of the k plus 1th instruction. Okay. So, instead of writing it as tuples, I have written it as pairs. Yeah. So, except when the precondition of the next instruction is different, or I need to prove some logical consequence, or so on and so forth. So, you can think of these downward implication signs as essentially the use of logical consequence, and whatever precedes this statement is the precondition. So, this is the precondition, and notice that the assignment rule, if I start with a precondition which does not involve anything to do with the variable that is being assigned. Yeah. Yeah.
So is the in mapping to natural numbers of beta, is it compulsory? Like,
it is not compulsory.
So if it maps to real numbers, then it
No. The choice of beta has to be done by the programmer. Okay. It cannot be mapped to the real numbers, because the real numbers are not well ordered. By a well ordering, I mean I'm actually, for all practical purposes you can think of it as a discrete set, not a set which is got it cannot. So, even if you take, let us say, the non-negative real numbers, The non-negative real numbers have a lower bound, but any open subinterval within them does not have a lower bound.
So if it is the non-negative real numbers.
Yeah. So what it means is that those kinds of bound functions do not guarantee anything, because you are not getting a well ordering. Okay. So the whole point is that your programming language uses discrete steps, and so you have to ensure discreteness and a well ordering, which so what are we saying now? By when we say a well ordered set, we are actually saying that you take any element in that well ordered set, there does not exist an infinite descending chain to the bottom. Okay. Whereas you take the non-negative reals, even though they are bounded from below, there exists a lot of infinite, from any positive real number there are more than a countably infinite number of length descending chains. So that is not valid. When I say well ordering, I mean that all descending chains have to be finite, they cannot be infinite. The set itself can be infinite, but from any particular point on the set you cannot do an infinite descent. Okay. Now that automatically throws out the reals. And once it throws out the reals, I mean you could use rationals if you like, but you know that also throws out. In fact, you cannot even use dense sets. Okay. So you have to use discrete sets, but then any discrete set would just be at most countably infinite, and therefore there is a mapping into the naturals. Okay. So that's what happens. So what usually happens is that I mean, if I'm this programming language, of course, is actually independent of the domain that we are considering, right? So as I said, I mean, you might just be doing manipulating lists of, let's say, characters or integers or some such. Lists of characters, and there might be no notion of integers. But your bound function is still somehow related to the structural inductive properties of the list, right? And there has to be a finite bound always. You cannot descend infinitely. That is the point. Yeah. So your well ordering could be some structurally inductive structure which is not necessarily the naturals. But if it is well ordered, then I can provide there is a, through Zorn's lemma and various things, you can actually provide a mapping into the naturals. Yeah. So that's not a problem. Okay. So in the case of so in this particular case, of course, what we are going to do is our measure is going to be just one of the variables itself, the variable that is decreasing, right? I mean, so it's as simple as that. But so here what happens is, okay, let's look at this assignment. So essentially, if I take this to be psi, then what we are saying is the precondition should be something that such that if I replace all free occurrences of p by 1 by this one, then I get something that's true. So actually this one actually is x equals x naught implies x equals x naught and 1 equals 1. So there is an implication there. So I am actually using the assignment. So that's this backward assignment is one of the most ingenious things that Hoare came up with. What is known as the backward rule for assignment, and that is essentially this, right? So this essentially works out to 1 equals 1 if you look at the assignment rule, which says that I replace all free occurrences of this of p in this predicate by this term 1. And when I replace all free occurrences of p in this predicate by this term 1, I get 1 equals 1, and that's a trivial tautology, right, of first order logic with equality on terms. Yeah. Okay. And of course, then we have this, right, which is, so if x is greater than or equal to 0, then my invariant property essentially says that I take p anytime and take the factorial of x, and I should get the factorial of x naught prime. And initially that is true. In fact, your initialization for p is guided essentially by that. Yeah. So that by the identity element for multiplication. So this is true, and of course, if x naught is less than 0, then of course we are setting p equals 1. Yeah. So I am taking the technically complete total correctness specification that I mentioned earlier, and what I am going to do is I am going to essentially prove that prove this post condition. If x naught is greater than or equal to 0, then p is equal to factorial of x naught, and if x naught is less than 0, then p is equal to 1. I am going to prove this as the post condition. And in order to prove this, I am finding all these kinds of logical consequences which would somehow help me come up with an invariant property, because I have got a loop here, right. So I require a loop, I require an invariant property for the loop. So I have to find various kinds of logical consequences. I have to massage things in such a way that I can get my invariant. One thing is, if you look at this, this predicate x naught less than 0 arrow p equals 1 is and x naught equals x here. Okay, I am sorry. This x naught equals x should go. I am sorry. This phi naught. Oh, okay. So let me take this phi naught. This phi naught does not mention x anywhere, and if x naught is greater than 0, greater than or equal to 0, then anyway this predicate x naught less than 0 arrow p equals 1 is trivially true. Okay. So this phi naught is actually anyway going to be invariant of this loop. It is not going to change in this loop. Its truth is not going to be altered in this loop. So I factor out this phi naught here, and here since x naught is equal to x, I can actually write this. Yeah. And I have therefore phi naught, and x is greater than or equal to 0, then p multiplied by x factorial is x naught factorial. When I have this condition x greater than 0, then I can make that a conjunct of this, and when I make that a conjunct of this, I get x is greater than 0 and p multiplied by x factorial equals x naught factorial. Okay. And what I am going to do is, and what I am saying is, part of the logic, and this actually, this whole predicate phi naught and this x greater than or equal to 0 arrow p star x factorial equals x naught factorial and x greater than 0 together actually implies this whole thing. And I have brought it brings in the bound function also automatically, because my bound function is just the variable x, the value of the variable x. Yeah. So the x greater than 0 ensures that my bound function, I have got only two variables in the program, x and p, and I am defining my beta of x and p to be just equal to x, and that is anyway greater than 0. Here of course the red 0 and the violet 0 are the same 0, they are both the same brown 0, right. That is because it is an integer program. But okay, so if this condition is true, then this is what I am going to keep as my sort of invariant property. Everything other than the red is the invariant property, right. So now when I look at this assignment, so I am going to do these two assignments. So look at this assignment, p is assigned p star x. So what we are saying here is, so take this condition and replace p by p star x, right. That is what your assignment goes backward from the post condition to the precondition, right. If you replace p by p star x and you have got x minus 1 factorial, then by the associativity of multiplication you get p star x factorial equals x naught factorial, right. Okay, so this holds, but the invariant doesn't necessarily hold. Okay, so what happens here is that I am replacing. So if you take here p star x factorial x naught factorial, then if I replace this assignment is x is assigned x minus 1, right. So, if I replace x by x minus 1 syntactically, then I get this one. Okay. So, notice that in this case I have maintained this invariant portion. This is this phi naught and x greater than or equal to 0 and p star x factorial equals x naught factorial is the invariant phi, and that is maintained from here to here. In between, because of these updations, the invariant gets partially destroyed and then it gets restored. So, in fact, here this invariant property is got destroyed because I have x minus 1 instead of x, but then doing the assignment x is assigned x minus 1 restores the invariant. So, inside the loop, the invariant can get destroyed and restored, but at the end of the loop, before you go back to checking this condition again, that invariant has to hold, and it does hold. As far as termination is concerned, what we have ensured is that the bound function reduces by at least 1. And the entire theory of proving programs using invariants essentially requires this. At the start of the loop, you have to define an invariant, a strong enough invariant. Before the end of the loop, that invariant has to be restored, even if it gets destroyed in between. So, this ensures that this loop with this precondition and this post condition is perfectly correct, right. And of course, this post condition implies this the post condition of the actual program that we want. So, you using the consequence axiom, consequence rule in order to show that this program is totally correct. So, this is the formal basis by which you have to do program verification. In a typical programming course where there is not any first order logic, what we usually do is we say you should look for an invariant property, a strong enough invariant property, and you should look for a bound function. And you have to at least intuitively argue that your bound function decreases with every iteration. And usually in a typical programming course, we take the bound function to be in the naturals or some naturals or some such thing, or some finite subset of integers, yeah, or at least a subset of integers bounded below. And that invariant property, normally I explain it as saying it essentially gives you a conjunction of two things. How much work has your loop already done? How much more work is left to be done? So, this bound function, how much work you have already done is what this invariant tells you, and how much work possibly needs to be done is what this bound function tells you, right. This bound function essentially gives you an upper bound on the amount of work you may have to do, and that is the number of iterations left is at most bounded by that, yeah. Okay. So, this is the rest. I think you should go back to your original programs and write some trivial programs and see that you can come up with invariants, even if you couldn't come up with them in CSL 102. At least now, in the light of fresh intuition, maybe you should try to do it. And by the way, all these rules have been applied exactly syntactically. Where the syntax varies, we have to prove logical consequence. Okay, completely syntactic. Remember that. Yeah, that is important. That's something that we don't normally emphasize in programming because that takes too much time. But for small programs, if there's completely syntactic, what it means is that you can actually do a backward movement from the post condition to some precondition and then farm out the corresponding, these are known as verification conditions. These logical implications which use the consequence rule are called verification conditions. So, basically what you want to do is you want to go through these rules syntactically driven and come up with all kinds of predicates. Then you have a specification which is some phi and some psi, and you have to prove what are known as verification conditions. You have to prove that that precondition implies whatever precondition you have calculated syntactically, and whatever post condition you have calculated syntactically implies the post condition that is given. So, those two verification conditions have to be farmed out to, let us say, a first order theorem prover, independent of the program. So, the two modules remain independently. There is a syntactic engine which just does a brute force propagation of through the rules of post conditions and preconditions, and finds and essentially annotates every line of the program. And then the connections using logical implications are all farmed out separately to a theorem prover. Okay. So, that is what happens. Talking about an open problem, a lot of you after 4th year will have lots of time in your hands. In fact, you will have the rest of your life in your hands. So, so maybe you should spend some time thinking about this. It is called the COLLATZ problem, and it was actually defined by a Dutch mathematics student, and it is a very famous open problem in number theory. But actually what this problem is that it's just worded as an iterative program. You can think of it as a while program. So, what you are saying is you take a positive integer greater than 1. Okay, I mean, if it is 1, there is nothing to be done. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Okay. Do these operations repeatedly. Okay. And the conjecture is that it will always terminate with 1. This process cannot be infinite. Okay. So, dividing by 2 reduces, takes you down your well ordering, but multiplying by 3 and adding 1 makes it even. You can think of it as multiplying by 3 and adding 1 and dividing by 2 also as one operation, if you like, but that takes you up the ordering of the naturals. So, it is a sort of fluctuating thing, and the conjecture is that it cannot do that forever. It has to come down to 1 at some point. Okay. So, this is called the COLLATZ problem, and basically what is this? This is a simple single while loop, that is it. Yeah. While so, if x is even, x is assigned x div 2. If x is odd, x is assigned 3x plus 1, and now what you are saying is find a bound function which will ensure that it terminates. That's really what you are looking at, and the whole thing is within first order number theory. I mean, there is, at the moment, at least from the point of view of the problem, there isn't anything more than first order number theory you require, because the signature you are using is very simple. You are just using the successor, and you are using division by 2 and multiplication by 3, that is it. So, you are doing something very trivial. It is a very trivial program, but because of those fluctuations, it is not clear what patterns those fluctuations take place. So, it's been an open problem for over 100 years, and it's not clear what kinds of techniques should be used to prove that this converges to 1 always. Okay. So, those of you who are on the threshold of graduation, I mean, you can spend the next 50-60 years trying this out. I think you will have plenty of time to try them out. And I will formally call the course closed now. Yeah.